Hey, Harsh here. Today we're going to talk about DNS. To understand why DNS is complex, you have to understand the problem itself. Back in the ARPANET days, if you wanted to talk to another computer, you looked up its address in a file called host.txt. It was literally a list. Every time a new computer came online, a guy at Stanford had to update the file and everyone else had to download it. It didn't scale, and in 1983, Paul, I don't know how to pronounce his name off, proposed a distributed system. Instead of one file, we broke the namespace into a hierarchy. This allowed decentralized management. You manage your slice of the internet, I manage mine. DNS is strict about hierarchy. We read it right to left. When you see www.google.com, the system actually sees the dot, then com, then Google, then www. That dot at the very end is the root, is the silent anchor at the end of every fully qualified domain name or FQDN. Below that, we have top level domain names like .com, .org, .in, .uk. These are managed by registries. Below that, second level domains like Google, this is specific to our organization. And below that, subdomains like www, mail, blog, these are defined by the domain owner. This hierarchy is critical. It dictates exactly which server knows what. It delegates authorities downwards. There are four servers you need to memorize. First is the DNS recursive or recursive resolver. Think of it as a librarian. This is usually provided by your ISP or a public service like Cloudflare 1.1.1.1. It receives queries from your browser or the OS and does the legwork for you. And then you have a root name server, the index. It doesn't know the IP, but it knows where all the TLD servers are. The TLD name server, it manages specific extensions like .com and points to the authoritative server. Finally, the authoritative name server is the source of truth. It holds the actual records and IP addresses for the domain. It is the final destination in the query check. Think of it like your resolver is your personal assistant. You ask them to find your phone number. They ask the root, the phone book distributor, who points to them to the TLD, the regional office, who points to the authoritative server, the local switchboard. Let's trace the packet step by step. You type example.com and hit enter. First, the browser checks its cache, then the OS checks its cache, and then the host's file. If all are empty, it sends a query to your recursive resolver, maybe your ISP or a public DNS like 8.8.8.8. The resolver doesn't know either, so it asks the root server where is .com. The root returns the IP of the .com TLD server. Resolver asks the .com TLD server, where is example.com. The TLD returns the IP of the authoritative server. The resolver asks the authoritative server, what is the IP of www.example.com. It gets the A record containing the IP address. The resolver then caches the IP for the future use and sends the response back to your browser. This entire chain happens in milliseconds. A recursive query is like telling your assistant, get me a pizza. You expect the pizza. An iterative query is like asking a stranger, where's the pizza place? They point down the street. Your computer makes a recursive query to the ISP. The ISP makes iterative queries to the root and the TLDs to find an answer. DNS lives on port 53. It usually runs over UDP because it's fast and has low overhead. Speed is critical for DNS and UDP is fire and forget. UDP packets were historically limited to 512 bytes. But if the response is larger than 512 bytes, like a big list of IPv6 addresses or cryptographic keys for DNSSEC, the server sets the TC, the truncation bit, in the header. The client sees this flag and retries the connection using TCP on port 53, which can handle the larger payload. TCP is also always used for zone transfers since zone files can be huge. Worth noting is modern extensions like EDNS0 allow larger UDP packets now, but 512 byte rule is the historical basis you will see in documentation. If you capture DNS packet in Wireshark, this is what you will exactly see in the 12-byte header. Let's break down the key fields. The ID is a 16-bit field that matches requests to responses. This lets your computer know which answer belongs to which question. The QR bit tells you if the query 0 or response 1. Opcode tells you the message type. 0 is standard query, 4 is notify, 5 is update. Now the flags. The AA, authoritative answer, bit is crucial. If it's 0, the answer came from a cache somewhere. If it's 1, It came straight from the source, the authoritative server. The TC bit indicates truncation. Response was too long for UDP. RD is recursion desired. The client is asking the server to do the work. RA is recursion available. The server saying, I can do that. And R code is the response code. 0 means no error, but R code 3 or NX domain is a technical way of saying that the domain doesn't exist. The A record is the bread and butter of DNS resolution. It maps the host name to a 32-bit IPv4 address, like pointing example.com to a IPv4 address. But we ran out of IPv4 addresses, right? Enter the quad A record. It maps a host name to 128-bit IPv6 address. Why quad A? Because IPv6 address are 128 bits, which is 4 times larger than 32-bit IPv4 address. Hence 4 A's. Clever naming. You can have multiple A records for one name. This is called round robin and it provides basic load balancing. The client cycles through a list of IPs. Also notice the TTL value in those records, that 3600 means this record can be cached for 1 hour before needing a refresh. CNAMEs are like C also in library card catalog. If you look up the rock, it says C. Johnson Dwayne. C names point a name to another name. But the main thing is you cannot put C name on your root domain like google.com. It breaks the protocol because the root needs on other records like SOA or MX. The TTL or time to live is a value in seconds dictating how long a record stays valid. When you set TTL to 3600 seconds, you are telling every resolver in the world, remember this answer for 1 hour. Here's how the caching layers stack. First, your browser cache. Chrome stores DNS for about a minute. Then OS cache, your Windows or Mac stub resolver. Then the recursive resolver at your ISP, which caches the full duration of the TTL. If you want to change the IP address 5 minutes after setting that record, nobody using those caches will know until the cached copy expires. This delay is what we call propagation. That is why DNS changes aren't instant. You're waiting for caches worldwide to clear out the old data. Let me first clarify what a zone is. It is an administrative boundary. For example, example.com and blog.example.com could be in different zones with different managements. Large companies don't rely on one server, they have a primary or a master server and multiple secondary or slave servers. To keep them in sync, they perform zone transfers, moving the DNS data from primary to secondary. There are two types. AXFR is a full zone transfer, copying everything. IXFR is incremental, copying only changes since the last sync. This is a heavy operation of transferring files, so it happens over TCP and not UDP. Usually we go from name to IP, but sometimes, like when a server receives an email, it wants to check if the IP sending is legitimate. It does a reverse lookup using a PTR record. If you are running a mail server and don't have a PTR record, Gmail and Outlook will almost certainly reject your emails. DNS was built for trust, not security, and attackers exploit that. Let's cover the main attacks. Cache poisoning is the classic attack. An attacker races the real server. If they get a fake answer to resolver before the authoritative server does, the resolver caches the fake IP. Now everyone using the resolver goes to the hacker's site instead of the real one. Imagine a bank clone stealing credentials. The Kaminsky attack was a famous variation exploiting predictable transaction IDs. DNS hijacking is when malware or rogue ISP changes your DNS settings entirely, redirecting all your traffic. DDoS amplification is another kind of attack in which attackers spoof a victim's IP address and send queries asking for large records from open resolvers. Those big responses flood the victim, and DNS tunneling encodes data inside DNS queries to bypass firewalls used for data exfiltration or command and control channels. DNSSEC fixes the trust issue by adding digital signature to DNS. Think of it as adding a signature to the phone book to prove it's authentic. The purpose is verifying the authenticity of data, preventing spoofing attacks. Here's how it works with cryptographic signatures. 3 new record types. RR-SIG is a digital signature of the record itself. DNS key is the public key used to verify that signature. DS or delegation signer is the link in the chain of trust passed down to the parent zone. When the resolver gets an answer, it checks the signature for the DNS key. If they don't match, it drops the packet that someone has tampered with it. The chain of trust follows upward. The root signs the TLD signs your domain. This creates an unbroken cryptographic chain you can verify all the way to the root. For about 30 years, your ISP knew every site you visited because standard DNS is plain text UDP. Anyone eavesdropping your network, ISPs, coffee shop hackers, government can see every domain you query. Recently, we got two solutions: DOH, DNS over HTTPS, encapsulates DNS inside HTTPS traffic on port 443. It looks exactly like regular web traffic, making it indistinguishable from loading a web page. DOT is DNS over TLS, which encapsulates DNS in TLS, and on dedicated port 853. It's secure channel specifically for DNS. Both encrypt your queries so nobody can see what sites you're looking up, but the trade-off is it is a headache for network admins. Corporate firewalls and parental controls rely on seeing DNS to filter malicious sites or inappropriate content. When DNS is encrypted and it looks like any other HTTP traffic, filtering becomes much harder. We covered a massive amount of ground. If you take anything away, remember the hierarchy. DNS is a distributed database where authority is delegated downwards. Remember that caching is what makes web fast. Hey, if this video helped you understand this topic, don't forget to like and subscribe. You can also drop your suggestions down in the comments about the improvements and the topics you would like me to cover next. Till then, thanks for watching, and I will see you in the next one. Peace.